This is SpaceTime Series 29, Episode 69, for broadcast on the 10th of June 2026. Coming up on SpaceTime, evidence of planetary destruction in the early solar system, are we missing a planet? And SETI, the search for extraterrestrial intelligence, investigates interstellar comet 3I Atlas. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Scientists have confirmed a cosmic collision in the early solar system which saw the complete destruction of a planet possibly as big as Mars. The findings, reported in the journal Earth and Planetary Science Letters, are based on an angrite meteorite fragment uncovered in the Sahara Desert, which was catalogued as Northwest Africa, or NWA 12774. One of the study's authors, Aaron Bell from the University of Colorado Boulder, says it's the first definitive evidence that this lost planetary embryo or protoplanet existed, and its unique geological makeup challenges long-held assumptions about how planets evolve. Bell says we know this planet existed because a few shattered fragments from its remains happened to land on Earth. And these meteorites preserved evidence of a completely different pathway through which planets can develop. Angrites are among the oldest known volcanic rocks in the solar system, forming within the first few million years after the solar system began some 4.56 billion years ago. They're also exceptionally rare. Out of the more than 80,000 meteorites discovered on Earth so far, only 68 are angrites. What makes angrites especially puzzling is their chemistry. Unlike Earth, Mars and the other terrestrial rocky planets, angrites contain very little silicon dioxide or silica, which is the main ingredient in nearly every known terrestrial planet in the solar system. For this reason, scientists figured angrites always come from asteroids, something with a radius of less than 200 kilometres. When Bell and colleagues began studying NWA 12774, they found the meteorite contained clinopyroxene, a mineral crystal commonly found in Earth's crust and mantle. But NWA 12774's clinopyroxene was especially rich in aluminum, a telltale sign that this rock must have formed under enormous pressure deep underground. So the authors then replicated the pressure conditions in the lab to determine what would be needed to form it. They found the aluminum-rich clinopyroxene needed at least 17.5 kilobars of pressure. Now, for comparison, the crushing pressure at the bottom of the Mariana Trench, the deepest point on Earth, is only around 1 kilobar. So that level of pressure simply couldn't have existed inside a small asteroid. Instead, the calculations suggest that the body where the angrites came from must have been at least 2,000 kilometers wide. And other clues in the meteorite point to an even more striking possibility. The crystals still preserved sharp edges and delicate chemical patterns that would normally have been erased if they had formed deep underground. And that suggests that these crystals likely formed at relatively shallow depths inside the parent body. And that implies that the world they formed on must have been even larger. Now, under that scenario, the angrite parent body must have stretched beyond 3,600 kilometres in diameter. That makes it comparable in size to the Earth's moon, possibly even approaching Mars size. Now, it's still unclear how the protoplanet met its end. One possibility is a catastrophic event in the early solar system which shattered it, its fragments later becoming the building blocks for other terrestrial worlds, including the Earth. Bell says the materials that form the angrite parent body are fundamentally different from the ingredients on Earth and Mars. He says it all points to a very distinct and separate evolutionary path in planetary formation during the early history of our solar system. This SpaceTime. Still to come, is our solar system missing a planet? And SETI, the search for extraterrestrial intelligence, investigates the interstellar comet 3I Atlas. All that and more still to come on SpaceTime. A new study suggests that one of our planets may be missing, and it could explain why our solar system looks the way it does. A report in the journal Icarus claims that this missing world might have triggered violent gravitational perturbations in the outer solar system billions of years ago that could have destroyed some of the moons orbiting around Jupiter and Uranus, while at the same time creating others. These calculations are all based on the Nice model of planetary migration, which was then refined with the Grand Tack hypothesis. In simple terms, it suggests that Jupiter and then Saturn were the first planets to form in the protoplanetary disk evolving around our still nascent Sun some 4.6 billion years ago. And they formed a lot closer to the Sun than where they are today, possibly around what today is the snow line, which is where the asteroid belt is today. The hypothesis suggests that as these gas giants grew, they initially began to migrate inwards, possibly to about twice Earth's current orbital distance from the Sun, before reversing course and moving out again, eventually ending up in their current orbits. Now, as Jupiter and Saturn migrated inwards, planetesimals in the protoplanetary disk were captured by Jupiter's resonance, causing the orbits of these tiny rocky bodies to shrink and their eccentricities to grow, resulting in a collisional cascade as their relative velocities became large enough to produce catastrophic impacts. As the density of these objects increased, it ultimately led to the formation of two major rocky planets, the Earth and Venus. The leftover material then formed the two smaller woods bordering them, Mercury and Mars. Meanwhile, as Jupiter and Saturn continued their migration outwards towards their current orbits, their gravitational perturbations flung material back towards the inner solar system, the evidence for which is clearly seen in the many craters on places like the Moon and Mercury. But the gas giants' migration outwards also caused more distant giant icy planets, which were forming at the time, to be pushed further away, with Neptune being flipped from inside to outside the orbit of Uranus in the process. And speculation has long suggested that there may have been a third ice giant, which was either destroyed during the migration or thrown further out beyond Neptune, possibly becoming a rogue planet, destined to float for eternity through the blackness of interstellar space. Now, according to this new study, the outer solar system experienced a period of extreme chaos, known as the Nice model instability, shortly after the planets formed between 4 billion and 4.5 billion years ago. And astronomers have long debated how the moons of these giants survived this violent period. To try and resolve that issue, scientists carried out computer simulations to try and model what actually happened. They analysed 122 computer simulations using thousands of different parameters to track the complex gravitational interactions between the Sun and the various planets, moons and large asteroids over billions of years, in order to see which models would evolve into the sort of solar system we see today. Now, the authors tested simulations included not just the 4 known giant planets, Jupiter, Saturn, Uranus and Neptune, but also scenarios which included an additional 1 or 2 planets, as speculated in the Nice model. And these simulations showed that the survival rates of moon systems of both Jupiter and Uranus was extremely low, as little as 15%. When the additional planets moved close to Uranus, the immense gravitational perturbations almost guaranteed the destruction of its moons. But rather than being flung out into space, they collided with each other, creating a massive debris field of ice and rocks. Now, over time, these remains accreted together, and that could explain how Uranus's oddly jigsaw puzzle-like moon Miranda could have formed. The simulations also show how these collisions could explain how Uranus ended up being tilted onto its side. It's a fascinating exercise, and it goes a long way to explaining much about how our solar system looks today. This is SpaceTime. Still to come, SETI, the search for extraterrestrial intelligence, targets the interstellar comet 3I Atlas. Could it have been an alien spacecraft? And later in the science report, does reading stuff on paper help you better understand it than reading it on a digital device? All that and more still to come on SpaceTime. This episode of SpaceTime is brought to you by NordVPN, SpaceTime's official VPN service. Let's face it, these days your online privacy is more important than ever. Whether you're streaming science documentaries, reading the latest research, or exploring deep space images, you don't want your data to be tracked or your location exposed. With NordVPN, one click is all it takes to secure your internet connection. It encrypts your data, hides your IP address, and keeps your activity safe from prying eyes, whether you're at home, work, or connected to a public Wi-Fi. And here's where it gets really good. As a SpaceTime listener, we have an exclusive offer for you. 74% off a NordVPN plan plus 4 extra months for free. That's right, a huge 74% discount plus 4 bonus months just for being a SpaceTime listener. All you need to do is head over to nordvpn.com/StuartGary. That's nordvpn.com/StuartGary. Not only does NordVPN protect your data, but it gives you access to content from right around the world. If you want to watch a science series that's only available in another country, no problem. Just switch your virtual location and unlock it instantly. And of course, the whole thing is risk-free with a 30-day money-back guarantee. So you've got nothing to lose and your online freedom to gain. So protect your digital life, support SpaceTime, and grab our exclusive offer now at nordvpn.com/StuartGary. That's nordvpn.com/StuartGary. The Search for Extraterrestrial Intelligence SETI Institute says it's found no evidence of any alien technology associated with the interstellar comet 3I Atlas. First detected back in July 2025, Comet 3I Atlas is the third confirmed interstellar object detected passing through our solar system. Now, astronomers know it came from beyond our solar system because of its hyperbolic trajectory and its high velocity of more than 58 kilometers per second as it entered the solar system. Comet 3I Atlas follows the earlier detections of interstellar objects 1I Oumuamua, that was in October 2017, and 2I Borisov in August 2019. Recent observations have shown that Comet 3I Atlas contains low trace amounts of heavy carbon in its coma, indicating it could be as much as 10 to 12 billion years old. Now, that's not only older than our solar system, it's almost as old as our entire Milky Way galaxy. Also, 3I Atlas is carrying unique chemical signatures indicating its origin in a distant corner of the galaxy in an environment drastically colder than our own solar system, likely near 30 Kelvin, that's minus 243 degrees Celsius. It has a deuterium to hydrogen ratio some 40 times higher than Earth's oceans and 30 times higher than native solar system comets. Astronomers have also detected methane gas readings alongside exceptionally high concentrations of both carbon dioxide and methanol. 3I Atlas entered our solar system from the direction of the constellation Sagittarius towards the galactic center. It reached its closest approach to the Sun back in October last year, swooping around our local star between the orbits of Earth and Mars. The comet then made its closest approach to Earth on December the 19th at a distance of around 270 million kilometers, and has just passed the orbit of Jupiter and is now flying through the constellation Gemini as it heads back out into interstellar space. Following speculation from all the usual suspects that 3I Atlas could be an alien spacecraft because of its unusual characteristics, all of which can be easily explained by its interstellar origins, the SETI Institute decided to undertake a detailed study of the object, as the Institute's Beth Johnson explains.
Scientists at the SETI Institute searched for technological signals from 3I Atlas, the third interstellar object observed in our solar system. Using the Allen Telescope Array, ATA, at the Hat Creek Radio Observatory in Northern California, the team scanned a wide range of radio frequencies for signs of extraterrestrial technology and found none, as expected based on other astronomical observations showing that the object exhibits natural comet-like composition and behavior. Its interstellar origin makes 3I Atlas a rare opportunity to study material from another stellar system and better understand how planetary systems form and evolve. While observations strongly indicate that 3I Atlas is a natural object, interstellar visitors are also compelling technosignature targets because an artificial object, however unlikely, could represent detectable extraterrestrial technology and potentially provide the first evidence of life beyond Earth. Eventually, our own Voyager spacecraft will be extraterrestrial artifacts in other stellar systems. Given that, it is important that we understand the natural distribution of interstellar objects so that we will be able to identify any anomalies that could one day be signs of an artificial interstellar object. The team observed 3I Atlas for more than 7 hours with the ATA, covering 1 to 9 gigahertz. This broad range allows scientists to search for narrowband radio signals, which are not produced in nature and would be evidence of technology. The team identified nearly 74 million narrowband signals. After removing human interference and filtering for signals matching 3I Atlas's movement, only about 200 remained for review, all traced back to technology on the surface of the Earth or our own Earth-orbiting satellites. While no technosignatures were found, the study sets new constraints reinforcing that 3I Atlas is a natural object. The observations place upper limits on the power of any radio transmitter on or near 3i Atlas, ruling out signals stronger than about 10 to 110 watts, approximately the power of a household appliance, over the detected frequencies. The results from 3i Atlas show how realistic it is to detect a signal with the technology we have today. That is why it is important to keep searching for technosignatures, even from objects we might not expect to have signals. Besides searching for signs of intelligence, the observation of interstellar objects also helps scientists learn about the natural properties of interstellar objects as they travel through our solar system.
That's the SETI Search for Extraterrestrial Intelligence Institute's Betty Johnson, and this is Space Time. And time now to take another brief look at some of the other stories making news in science this week with a science report. A new study by the World Meteorological Organization warns that global average surface temperatures are likely to continue at or near record levels over the next 5 years, with next year, 2027, likely to set new records. The report predicts that the 2026 to 2030 period is likely to range from 1.3 to 1.9 degrees Celsius in temperature above pre-industrial levels. And there's an 86% chance that next year will surpass 2024 as the warmest year ever recorded thanks to the El Niño, which is now upon us. The study also found that there's a 91% chance that global average near-surface temperatures will temporarily exceed 1.5 degrees Celsius above 1850 to 1900 levels for at least a year between now and 2030. A new study has discovered 2 distinct subtypes of autism with different underlying biology. The new findings, reported in the journal Nature Neuroscience, used brain scans to identify distinct patterns of brain connectivity in autism to different underlying molecular mechanisms. The hyperconnectivity subtype involves areas of the brain communicating more than usual, while the hypoconnectivity subtype involves reduced communication between brain areas. The authors claim that together these subtypes account for approximately 25% of individuals with autism. The findings are based on scans analysing functional connectivity across 940 children and young adults with autism and over 1,000 neurotypical individuals. The 2 subtypes exhibited different functional brain architecture and showed modest differences on standardised autism assessments, with the hyperconnectivity subtype scoring moderately higher on autism severity measures. Meanwhile, a major British study has found that while most middle-aged and older adults experience low levels of anxiety, a small subtype of people, those with higher autistic traits, are more likely to report that their anxiety worsens as they age. The findings, reported in the journal Nature, highlight the lack of research in older people on the spectrum, 90% of whom have never been formally diagnosed. A new study claims reading stuff on paper might help you better understand the subject than simply reading it on a digital device. The findings, reported in the journal PLOS ONE, looked at brain scans of people who were first asked to read an item on paper and were then made to swap over to a digital device to finish the item. The participants were then asked questions on each half after finishing. The authors found participants took longer to think of the answers after reading on the tablet compared to reading on paper. Additionally, areas of the brain known to be related to language that were activated during reading on paper were significantly less active during the digital half of the experiment. NVIDIA's new RTX Spark Superchip has stolen the show at the Computex 2026 trade fair in Taipei. Integrating CPU, GPU and up to 128 gigabytes of memory on a single chip, it'll power many of the world's upcoming flagship laptops. With the details, we're joined by technology editor Alex Zaharov-Reutt from TechAdvice.life.
This is Computex in Taipei, in Taiwan. It happens every year. It's the biggest trade show for Asia, focused on the West, and all the major companies are there. All the major PC makers, AMD, Intel, Qualcomm would be there as well, but also NVIDIA. Now, NVIDIA is what powers the GPUs and the AI chips that are sitting in all those multi-billion-dollar data centers. And NVIDIA has designed a chip that can sit inside of a Windows laptop, which will come from people like HP, Lenovo, Dell, and others. And this is the new PC. This chip is called an RTX Spark, and it's a super chip that combines the CPU, the central processing unit, of course, the GPU, the graphics processing unit, and will have incredible neural processing capabilities because it's the NVIDIA chip that is effectively powering this AI revolution. And what it's designed to do is give your computer the same kind of AI powers that you get in the big data centers. And that's where AI is heading. AI is going to become local. You won't have to spend hundreds of dollars on tokens or subscriptions to Claude or ChatGPT or Gemini because your computer itself will be able to do offline AI. Now, online AI is always going to be more powerful because they have huge clusters of these incredible GPUs strung together. But these sorts of super AI chips that NVIDIA is working on is also going to become the brains of physical AI, which is a fancy way of saying robots. So that is going to be a new class of computer. It'll run Windows 11, but it'll have all these agents and you can talk to it. You'll be able to talk to it and converse with it like you can with AI today, but your computer will then do things on your behalf. And, you won't have to click on buttons anymore. You'll just ask for things to be done. So it's a big change. I mean, it's sort of the same sort of
like Captain
change.
Kirk on the Enterprise.
Yeah, it's like Commander Data or talking to the ship. We did go from the keyboard to the mouse, and we had the VR headset, the augmented reality glasses. So NVIDIA is launching this new architecture at Computex, and it's doing big battles with Intel and AMD, who make the traditional chips that you find in computers, and also Qualcomm that has their ARM-based chips, and of course Apple has their ARM-based chips as well. Now, we're yet to see what Apple's going to announce at its big worldwide developer conference and how they will integrate AI into their platforms. And we also saw Dell launch a competitor to the MacBook Neo. So that's a computer that's $599, 8 gig of RAM, 256 gig SSD, running Mac OS using an iPhone A18 Pro chip. Well, the one from a couple of years ago, not even the one from last year. And yet it's selling in massive amounts. Apple can't make enough of them. People want to buy it. So Dell has come out with a computer for $699 US. Unlike the Apple, it has a backlit keyboard. It has a touch screen, not just a non-touch screen. And it comes with 8 gig of RAM as well, but you can upgrade it to larger amounts of RAM and SSD. So there's this push to bring PC prices down, to give you a chip that is more than powerful enough to do all the everyday tasks that people do, but still give you 17 hours of battery life, which is the sort of life cycle lifespan that Apple is talking about, for only $100 US more. And we should see more people competing in this space, but this is all happening at a time when the cost of memory and SSD is going through the roof.
That's Alex Zaharov-Reutt from TechAdvice.life. And this is Space Time. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from SpaceTimeWithStuartGary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to SpaceTimeWithStuartGary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.